Dim the lights a little bit back there. And can you just control the down button or the up button if I need it in case, because I'm not sure that my button is going to make a difference. Thank you. Yeah. Okay, folks. So the raffle sale has ended. Is that right, Ray?
Yes, I'm going to start.
You're doing your arithmetic. Thank you. So, can you think back for a moment to when you got started in ham radio? I can think back. It's a few years ago, at least 2 or 3. And I started my ham radio experience in 1952 as a novice. And I didn't have a clue as to what impedance meant. But quickly I got into the idea that a transmitter was somehow connected to an antenna, and we're asking questions related to that today. How does a transmitter connect to an antenna? What's the impact of the antenna upon the radio? So bear that in mind as we think about these things. Let's see if I can move this slide with this thing here.
Not that one. Not that one.
Not that one. Okay. Then
the one in your left hand. You got it. You already did.
This one do it?
You've changed already.
Yeah, he's pushing the buttons for me. Thank you. So we're going to be answering these questions, I hope, today. What are impedance and resistance? Obviously, as the name implies, they have to do with the freedom of electricity to flow in wires or antennas. And specifically, we'll look at an antenna in a minute, and we'll be defining in rather casual ways what the concepts of voltage and current and power are. If you want to ask more questions on that, please do by raising your hands. And I will share a simple mnemonic or picture for remembering Ohm's law that was shared with me years ago. It uses a triangle that's really pretty neat. And then why is impedance matching so big time in radio? We will not be talking in terms of SWR. We're not going to bring in a highfalutin SWR measurement device, but we'll be talking about that which would try to minimize SWR or make it as close to 1-to-1 as possible. And we will be using a very simple model. I brought in a model here. This little X box is not what the kids call X box today, but this will be our box. It's a source of energy with an internal resistance or a source impedance, and we'll be actually making measurements of it and showing the results of those measurements and the impact of changing the relationship between the load resistance or your antenna and the source resistance. That's the resistance that your transmitter has. And then we'll see what happens when we actually vary one of those things relative to the other. So let's see if we can move this slide on to the next one. Slide, please. Thank you. Okay, remember when we had the first session a couple of months ago, we showed a half-wave antenna? This is just reminding you of that. Notice that the solid curve at the top here, which represents the current flowing in this half-wave antenna, has a maximum at the feed point or the center and a minimum at the other end. And the voltage, on the other hand, is way high with this dotted curve at the left and the right end of this antenna. So the left and right hand ends are high voltage points. The center is a high current point. And so the relationship between the voltage and the current is what we call the impedance. The ratio between voltage and current is an impedance measurement. So look at the center there, for example. There the current is low. Pardon me, the current is high and the voltage is low. Current is high, voltage is low. So what's the ratio between voltage and current at the center? Is it low or high? Low there. So the center is a low impedance point. Whereas at the end, on the opposite end of things, where the voltage is high and the current is low, that quotient is what? High or low?
High.
High. So that's really a high impedance point. Good reason for having a good insulator at the end so that the voltage isn't shorted to ground or the trees or something around you.
Or kill you.
Or yeah, it can give you a good zap if you don't keep your fingers away. Right, you can pretty well touch the center of the antenna if you're careful, unless it's a high power radio. But so that's just a little relationship of how impedance has to do with the antenna, which has a standing wave in it. We're going to look at it in a simpler way. Next slide, please. So some of you had this in your first examination, perhaps. Ohm's law. Remember Ohm's law? Yes? And maybe you've seen these triangles before. I love these triangles. It's a nice way of remembering, in a simple way, a relationship that is pretty important in radio and other things, with electrical circuits. But you see at the top, the V stands for voltage. And in the center, you've got I, which for some reason represents current. It probably came from the French or the German. I've forgotten why I is a symbol for current, but it is. See, you have I and R next to each other there. So V is equal to, in the bottom, can you see V equals IR? Because I and R are next to each other. That's the basic Ohm's law. Yeah, you could use E. Some places they'll use E for electrical motive force. So that's the same idea. It could be E equals IR or it could be V equals IR. This is what I found on the web when I was making up this presentation. The units of electromotive force, which is usually the battery force, and voltage are the same. They're both volts. And so if you want to know the current in a resistance R that has a voltage V across it, is always I equals, see there's a line below the V? So it's a quotient between V over R, which is equal to I. Some of you like to play algebra, so you'll see how that came out anyway. Similarly, if you want to know the resistance that's bearing the current I and has a voltage V across it, then you see it's a quotient between V and I because there's a line below the V to give you the resistance. Question about that cute little triangle slide? Okay, well, I hope that helps some of us. It's been a good guide for me. Next slide, please. I have another little trick here. When I was teaching college physics, the power is defined as a product of two things. I, what's I represent?
Current.
Current. Thank you. It's the current, and the V represents the voltage. So the product of those two things, we could play with this lots of ways, but this is supposed to be brief. So P equals IV, or Princeton is Ivy League. P equals IV is a way of remembering that product. So if we have the definition of power, I want to express that power in terms of just one of these variables. It's easier for us to measure voltage today. I'm going to ask Henry, KH6VM, to help me with these measurements today on our little gadget. If we can just measure one of these things, either I or V, it's handy to measure the voltage only and then use Ohm's law to replace I with V over R. See how I've done this in the third line? Substitute for the current I, substitute the quotient V over R. And thus, thank you, Henry, the product of V squared, V times V over R, would give us the power in the resistor that we're going to apply it to. So we'll do an experiment with that. And before we do the experiment, Henry's hanging in there. I've asked him to help me out here. Next slide, please. How does it relate to radio before we go on to the next little thing that won't look like radio at all? Thank you for the next slide. Thank you, Don. This doesn't look like a radio to new hams, does it? But when some of you got into radio in the 50s and 60s, this looks like a radio. So this is a famous old 1950s or 1960s single tube radio transmitter, or oscillator and transmitter. The basic things to keep in mind are that everything to the left of this little antenna jack, see the antenna jack at the upper right? That's where you connect your antenna. And everything to the left of that, especially this coil that's called L1, and these two capacitors called C6 and C7, see those? That makes a pi network that matches the transmitting tube, the 5763's impedance with the antenna. It makes this look like 50 ohms, hopefully, to the outside world. Basically, this whole thing looks like a generator with a certain radio frequency voltage and an internal impedance that will be modeled in the next picture. But basically, this is an idea. So everything to the left of the antenna connection is a voltage and a resistance. So the next slide will show that simple model of the thing. Next slide, please. Thank you, Don. So this is a simple model. The source, you see the source to the left box? This is ridiculously simplified, but basically that transmitter you saw on the previous page was a generator of radio frequency voltage. In our experiment, we'll be just using a simple battery and a resistor, but the idea is the same. So you've got a generator in here with a series resistance. Internal device is 50 ohms in this picture, but in this experiment we're going to do that both of those things can be changed. So, but in this box, this X box, they will be fixed. And then the load over here in this picture is shown as matched because the 50 ohms in the load is the same as the 50 ohms in the device. And we're going to hope that our experiment shows that when those two things are equal, 50 and 50, you have maximum power transfer. In our cases, those numbers will be different. But we're going to have a source that is fixed, different from these things, but it'll be a little battery and a resistance, and then we'll vary the load resistance and see what happens. And I'm thanking Henry for helping me with those measurements. Ready for the experiment? Yep. Okay, so let's leave that on the current slide, and just leave that on for a minute. This is our source. Inside it is a DC battery. You'd recognize it. And inside it also is a little resistance. And we can make a connection to an external load here. I brought in several load resistors. A small, here you can see some resistances. This is a 220 ohm resistor. And then I brought in also a 1,000 ohm resistor and a 5,000 ohm resistor. So a low and a medium and a high resistance. And we're going to connect these. First of all, we'll connect these using the wires and the plugs, and Henry will measure the voltage using a regular DC digital multimeter. Here we go. So,
all right,
what can you measure? You're going to measure.
Okay, I got 1.68.
So somebody write down with a piece of paper, if you've got it, 1.68 volts with 220 ohms. 1.68 volts for 220 ohms. And if you use V squared over R, you'll calculate some watts. It's a so small number of watts that actually it's better to measure it in milliwatts. We're going to do this 2 more times. Anybody needs to take a snooze, feel free to do that right now. We're going to try it with two more resistances. This is with the medium, 1,000 ohms. I tried this with radio antenna. It wasn't as easy to do.
Yeah.
But so,
all right, in this particular one here, we got 4.7 volts.
Measure that, write that down, 4.73 volts. 4.73 volts for 1,000 ohm load. We're varying the resistance in the load now. It's like we're changing antennas. Maybe feeding this or connecting the end of the antenna to it. And then finally, very high resistance, a different antenna still, 5,000 ohms. Now Henry will do us a service of measuring again. Thank you, Henry. And that's measuring.
Okay, got 8.1.
8.1 volts for a load of 5,000 ohms. Well, what does that mean in terms of power? I'm sure you've all been using your calculators or doing it in your head to figure out the power in those 3 cases of a low, a medium, and a high load resistance. Low and medium and high with respect to what, you may be asking. And it actually has to do with the regard to this internal resistance of the source, right at 50 ohms. In our case, the source is not 50 ohms. The source has an impedance quite a bit higher, as you'll see. So the next slide will show you the results of the experiment. Thank you, Don. Oh, this is our box. So this is what we've been doing. That's your X box with an internal resistance and a battery, and then we've connected our R's to it. Question on what we've just done? 3 times. Yes?
Can all this stuff be like put on an attachment and sent to our email for like study purposes?
Thanks to David, it's going to be, the video and sound will be put on a link that's on the web.
YouTube, and it's a WA7 LAW YouTube channel.
Just go to the WA7 LAW YouTube channel, and it'll show you 1, 2, or 3 options for the first 3 presentations. Yes, thank you. Other questions so far? All right. Then the next slide, please. Heck you go. There you got it. Heck you. So here's the results of those. You see the 3 dots? Those 3 dots are the powers we calculated for those 3 loads, low, medium, and high. You see the horizontal displacement represents the load resistance. The vertical represents the power developed in the load resistance, which is what you want to have happen if you're curious about maximizing the power delivery to the load. You want to have maximum power delivery. So clearly we got a maximum at the 1 kiloohm, which I can tell you I cheated because I made this device. And it happens that the internal source resistance of this is 1,000 ohms. And at that point, it clearly equals the load resistance. So the main lesson for today is you get maximum power transfer when the load resistance equals the source resistance. And I cheated because the blue curve is plotted from an equation I didn't want to bother you with today, but it's an equation for the power developed in the load, given a certain source. This battery and this internal resistance. And it happens that those 3 dots are on the nice line, which, yes, it's a cooked up presentation, but that's what we did today, was to show the efficiency. And it happens if you're doing antenna matching to a transmitter that you would also have at that top point the minimum SWR close to 1 to 1 for other reasons that could be clarified. Questions so far? How do we do on time here today? What's the time? The time's okay? Okay, so it's about time for a raffle. Questions about the presentation? Oh, thank you. Thanks very much. Thank you. Yes, we're done with the slides. That can be deleted. Okay.
So we sold 105 tickets today, took in $88, so 44 of that will go to the lucky winner. I'm actually going to step over here to the new guy. Reach in there and grab a ticket.
I've got a 25-point learner.
The last 4 digits, 6115.
6115. Who has a ticket with 6115? Hey! Oh, Carrie. Way to go, Carrie. Nice job. And some of you newcomers may not know, but Carrie is helping to direct the new net for young ladies, or YLs, for the club. Is that Thursday evening at 7, Carrie?
Thursday evening at 7. It is.
Thursday evening at 7 on the club repeater, FM. Thanks very much to her and to all the participants.
Can you read out the YouTube channel again?
YouTube channel, go to YouTube, WA7LAW. Just the club's call sign. And it should present you with 2 options, and as soon as Dave can muster it, 3 options for a presentation.
Probably be tomorrow.
So, well, he works fast. Tomorrow. Thank you, David. Thank you all for your attention and for your participation in today's club meeting. Next month, the presentation should be by Department or Emergency Management official. And we look forward to that.